Greetings and salutations, my friends. Welcome to a pre-recorded version of my talk on Python's object/data model that I gave at the Python Guild at Gen Digital on the 14th of May 2024. Few words about me. I'm a tech lead / architect in Threat Labs for the Threat Intelligence Systems group, which has 26 people and 3 subteams. I've been programming in Python for the past 17 years, and I started programming in Python 2.5 in 2007, which, yeah, I guess it makes me really old. But just to put things into perspective, in Python 2.5, the support for context managers, the with keyword was newly added, and also the multiprocessing module was added there. And there were lots of talks about, all style classes versus new style classes and future compatibility with Python 3 and so on. I have written both small projects, medium projects, up to very, very large behemoths containing 2,000 lines of code. I am not an expert by any means, but I would say I have fairly advanced knowledge of Python. I enjoy writing about it, both on my Czech and English blogs, and also speaking about it and teaching it, primarily via invited talks at the Faculty of Information Technology, Brno University of Technology in the Czech Republic. My hobbies, obviously creating slides in LaTeX. And if you want to know more, just visit my website, the link is here. The talk is gonna be a live demo mostly, but I have prepared some slides so that we do not get totally off the track. If you want to check out those examples, here is a link to all of them on my public GitHub profile. So feel free to visit them either during or after the talk. Let's start with the definition of an object. So an object is an abstraction of data or real-world objects that are important to your script, program, system, what have you. And they have a state, which is defined by the data the object contains, and also behavior, which is defined by the code that manipulates the data. And in object-oriented programming, we have both data and code together, meaning that state and behavior together. So we have objects that manipulate their data. This is in contrast to procedural programming, like in the C language, where there are structures and we create those structures and pass them to functions. But the structures and functions are decoupled. What is an object model? It defines the characteristics of objects in a language. So to give you a few examples, are there just objects in the class, in the language, for example, like in the self-programming language, or are there classes, like in C++ or Java? And is there only single inheritance like in Java, or multiple inheritance like in C++ and Python? And how are objects constructed and destructed? And how does attribute lookup work? So all of that is described by the language's object model. And today we're looking at Python's object model. So the basics. Let me open this example. If you are listening to this, I can expect that you know everything that is in there, or at least the basics. What does it mean? So how to create a class, how to subclass the class, what is an initializer, what is a method, what is a property, what is a class method, how to instantiate a class, and how to call methods on it and access its attributes. If you are not familiar with the basics, I'm not sure whether the rest of the talk will be useful to you, but hey, it's your choice. Feel free to keep watching. One thing that is great about Python is very little of it is actually magic that would need to be hard-coded in the interpreter, and the language goes almost superhuman lengths to expose all its moving parts. So almost everything is expressed in types instead of being in language or in the interpreter. Of course, there are some costs associated to that. For example, there are performance costs, but if you care about raw speed and you're using Python, I'm afraid to tell you that you're using the wrong language. Also, another important thing, almost everything in Python is an object. And what I mean by that, let me fire up an interpreter. So for example, if I create an integer, I can then call methods on that. So for example, bit length gives me the number of bits that are required to store that integer. If I want to, I can directly call the method on a value like this one. However, in this case, Python would yell at me that this is a malformed floating point string. So I either need to put a space here, or I need to surround the number by parentheses. Both are okay. So there is no distinction between primitive and more structured types in Python. Basically, everything is an object. If I create a function foo, let's say in this way, then function is an object, so I can assign the function to another variable, and I can call that function indirectly like this. Or I can create a class in this way and also work with it like with any other object. Also, the 3 dots is an ellipsis object, which you might see in some examples, because as you might have heard, Python resembles executable pseudocode, and 3 dots are very expressive in this way. Also, you can mess with Python's bytecode. So if we have that function, we can access its bytecode object. If we want to, we can disassembly the bytecode using the dis module like this. Yeah, and we can work with the bytecode. We can create our own bytecode, but this is out of scope of this talk. Also, everything in Python inherits from a base class called object. So if we, for example, take a look at the base classes for integer, we see that an integer inherits from object. If we take a look at a dictionary, it also inherits from object. So in Python, every class hierarchy starts with an object. Every object has 3 things: an identity, type, and value. So an identity of an object can be obtained via the ID function. It returns an integer and it tells you a unique number for each object. And it is used when checking whether 2 objects are actually identical, meaning that they are the same object, or whether they are just equal. As an implementation note in CPython, this number is the memory location on which the object is stored. So if we create 2 integers, we see that they are equal, but if we check their whether they are identical, we see that they are not, because these are 2 separate objects. As a homework assignment, you can try to find out why some integers are identical, like these 2, and some are not, like these 2. So that's the identity. Then we have type. A type of an object describes what we can do with that object. So an integer has different methods than, for example, a list. So Python has types. They are important, but I would say that they are not that important like in some other languages, in statically typed languages such as C++ or Java, because in there you are more restricted of what you can pass around, what you can call on an object. Python is dynamically typed and it uses duck typing, meaning that it is important what the object provides, whether you can call something on it, not necessarily its type. And last but certainly not least, we have values. So if we have an integer, its value is obvious. If we have a list, then its value is the 3 elements in that list, and so on. So the value of the object depends on the object itself. Objects in Python are extensible, meaning that they do not have a fixed layout. Let me create a file. In here, we're gonna create a class like this. We're gonna store that integer, and then we will instantiate the class. Now I will load the file, so we have the A object and we can access its A attribute. If we want, we can start adding new attributes into the object, and we can also access those attributes. Also, we have that class, and if we want, we can even extend the class during runtime. So we can, for example, add a new function into the class, and then we can call it via an already constructed object during runtime, which can be useful. Okay, so now if you want to, or if you need to, you can even change the types or base classes at runtime. Although beware when doing so, because it can have some unexpected side effects. And also your colleagues might be like, hey, what you doing? This is like strange. Yeah, but Python supports that. So if you need this, it is possible. One exception is built-in types. So for example, integers. If I try to add a new attribute to an integer, this fails. Because built-in types are usually not extensible. Alrighty, let's take a look at how does construction and finalization work. So here we have seen this example. In Python, this is called an object constructor expression, and it is composed of two parts. One is the initializer, which takes an already constructed instance and initializes it. The other part is a new function, which basically whose purpose is to create an instance of the class that is then passed to the init function. So we're gonna just print new here to see that it is called. Then we are gonna print also init. And we are going to, offload the creation of an instance to the superclass, which in this case is object. And then this object is going to be passed here, and it will be initialized. So if I load the file, we see that new got called and init got called, and we can access the attribute. Now, you may be wondering, when would I want to use this? One example is when subclassing a built-in type. So for example, we would like to create a string called a string, stripped string, meaning that when we create it, it will be automatically stripped, meaning that its leading and trailing byte space is going to be removed. So we can do that by subclassing string, but as you know, string is immutable in Python, so we need to strip it before the initialization, because during the initialization we cannot change the string. So we're gonna use override the new method. Then we will need to strip the string. And we're gonna call the new from the base class to create the string. So if I restart this and we check out our string, we see that it was stripped. Now let me get back to the previous example, which is this one. And let's talk about finalization. There is a special method called del, which Python calls when the object is to be garbage collected. And you can override this method in cases you would like to, for example, close an open file descriptor, or open or close a socket with a network connection, and so on. The important thing is that this is called a finalizer, and this is on purpose because it is not a destructor, as it is implementation specific when the finalizer is called. So for example, when the interpreter ends, some interpreters might call this delete the finalizer, some may not. So do not rely on them like you would rely on destructors in C++ or Rust. If we delete the object here, and if we run this through the CPython interpreter, we see that the del was called, but this is because CPython uses reference counting, so it is able to immediately see that the number of references here is 0 and call the finalizer. If we use PyPy, which is another Python interpreter, it has a fully fledged garbage collector, and in this case we see that the delete method was not called. And final remark, we see that we didn't have to specify that this is a class method. It is actually a static method, and there is an exception that this is in the language that the new method is implicitly a static method. It is not a class method due to some technical reasons. Yeah, so just if you were wondering why we didn't have to include the class method decorator. Okay, as you probably know, Python supports multiple inheritance. So I took the liberty of pre-creating this so that I don't have to type it all at once. So we have a class hierarchy, and it is the classical diamond hierarchy, meaning that A is the base class. Then we have both B and C inheriting from A, and then D inherits from B and C. And we create an instance of D. So if we load the file, we have the D object, and obviously if we call D, if we call foobar, it obviously calls it from D. But if we call just foo, here we see that Python called the implementation from B. If this were C++, you would get an error during compilation, an ambiguity error, meaning that you would need to choose from which base class you want to call the function, because it is present in both cases. But Python has selected the implementation from B. Python uses the MRO attribute, which stands for method resolution order, to determine the order in which methods are checked. The naming is kind of a misnomer because it is used not only for methods but also for attributes. So in this case, we see that when accessing an attribute or calling the function, Python first tries the class D, which is the class of the object. Then it tries classes B, C, A, and then don't forget about our top-level object class. Python uses a so-called C3 linearization algorithm to create such a list for every class hierarchy. No matter how hairy or complex it is able to serialize it in this way. If you need, it is possible in Python to specify your own method resolution order. So you could theoretically use, like, I don't know, depth first search, or order the classes by their name. But once again, it is possible, but be careful when doing that. Okay, the final part of the basics from this slide is the difference between methods and functions. So let's start fresh, and let's create a class that has a foo method that basically, yeah, let's just return 42, and then we can create an object. So if we take a look at what a.foo is, we see that it is a so-called bound method, a.foo of our a object. By bound method, Python means that the self parameter of foo has been bound to the instance a. If we want, we can store that bound method in another variable, and when we call it, it will call foo where self is bound to a. On the other hand, if we take a look directly into the class on the foo function, we see that it is actually a regular function. And if we want, we can call it in this way, meaning that we can pass a as the self parameter explicitly, like this. By the way, when we have that foo method, we can determine the bound object through the self attribute. Yeah, and later we're gonna see how to implement methods using descriptors. Let's talk about how Python stores data. Python loves dictionaries, so we'll see that most of the things are stored in dictionaries. Let's start with an example. So we are going to create our well-known class A, instantiate it, and the file. If we want to check the state of an object, we can take a look at its Dict attribute. If we add another attribute to the object, we can see that it is stored in the internal dictionary, and we can modify the dictionary if we want to. Then also classes have dictionaries. So if we take a look at the dictionary of the class A, we can see that it is not a straightforward dictionary, but so-called mapping proxy, because the dictionary of a class cannot be directly modified. If you want to modify a class, you need to do it via sedator, like the example that we saw earlier with adding the foo function, but you cannot directly modify the dictionary of a class. So we see that there's the init method, there's support for so-called big references, docstring. As a homework assignment, you can try to figure out what is the Dict attribute in the Dict attribute of a class. And also functions have those dictionaries. So if we define a function, we can see that it has a dictionary. Or if we import a module like a multiprocessing, yeah, we can see that it is there. So it contains all the classes and functions from the multiprocessing module. If you know something about dictionaries, in Python they are implemented as a hash table, meaning that each object needs to have a separate hash table, so it can be memory inefficient if you have lots of objects. And also the lookup can be slow because each attribute access, if it goes through the dictionary, is translated into a hash table lookup. So if you have lots of objects, you can run into memory issues, meaning that you might not have sufficient memory. There is one way to handle that, and this is called slots. So what we can do, we can define the slots attribute on the class level, and it describes that instances of this class will only have the selected attributes. So in this case, this is A and B. So let's store it, fix this. And in this case, Python will allocate an array for these attributes and will not use a dictionary to store them. So if we load the file, we can access those attributes. But if we tried to, modify the object, we see that we cannot do that because we are only able to modify attributes A and B. Also, we can see that the A object does no longer have the dict attribute. So the benefits are twofold. First of all, it saves memory because instead of a hash table, you only need to create an array with the number of attributes that you need. And also, attribute access becomes faster because now what you need to do is to only index an array instead of doing hash table lookup. But there are also some disadvantages that you need to be aware of. First of all, instances of those classes are not extendable because they then don't have that dictionary. Also, if you have a class hierarchy that uses slots, you need to put those slots into every class because those slots do not propagate through class hierarchies. So if you want to use slots, you will need to use them in every class. Otherwise, Python will introduce a dictionary to a class which doesn't have slots. So you need to redeclare them in subclasses. And also, if you need to use weak references, this will not be supported. If you need that, you will need to add a weak ref attribute here so that Python can store them. But this is not important right now. So just that you are aware of that. Now you might be asking what happens when you try to access an attribute of an object. For this purpose, I like this blog post by Yonel, which has a very nice diagram of what is happening. Luckily, all of that is described in the Python documentation. And also what you see here is just the default implementation that Python provides. But if you want or need, you can override any of that and use your own implementation. I will not go through all that diagram completely. I will just mention some of the parts. We'll see this method in a short while. So first of all, there is handling of descriptors, which is here and here. We'll see what they are in a short while. So basically, first Python tries to access that attribute in the dictionary. If it is found there, it is used. If it is not in the dictionary, Python tries to look it up in the class. And if it is there, it uses it. If not, it checks the base classes. And also, if the attribute cannot be found, Python calls this method, which we're gonna see. So if you need, you can look it up in the documentation or in the blog post. It is referenced at the end of the slides. And we'll see more details shortly. Let's see the two methods that were shown in the diagram, getAttribute and getAtter. So let's clear that and that. So let's just use that A attribute here and here. If we want, we can hook into an attribute lookup for attributes that the object does not provide. So let's do a quick print statement here. And for example, we will choose that we just want to return 42. So let me load the file. Now, if we access A, it just gives us 1. But if you try to access a non-existing attribute, we can see that getAtter was called and we got that number. And this is the same for all the missing attributes. So if you want to react to accessing arbitrary attributes that are not in the instance, you can use getAttr. The other option is to specify get attribute. The get attribute method is called for all attribute accesses. So if you override it, be careful, because if you access self in this way, this will also call the get attribute, so you can easily stumble or get into infinite recursion. So if you need to access an attribute here directly, use the super implementation from the super class. In this way. So let's reload, and here we can see that even when we accessed an attribute that is directly in the instance, the get attribute function was called, and the base implementation is what it does is all of this that we see here. And of course, when we access a non-existing attribute, we see that first get attribute was called, and the machinery in the default implementation called getAttr, which got us that 42. Now, to conclude this section, let's talk about descriptors. Descriptors are the mechanism behind various parts of Python. For example, they are how regular methods are implemented, static methods, class methods, and also properties. And some people say that after you understand descriptors, you understand Python. And we're gonna see what those are, how those could be used, and some details. Okay, so what are descriptors? Descriptor is something that is supported by Python, and they can be thought as reusable properties. So if you know properties, descriptors will look very familiar to you. All right, so let's clean up and let me give you an example. So let's say that we have a class, and we will try to create our own descriptor in this way. Okay, so what we're gonna need is a class, and in order to create a descriptor, we have to implement either of these three methods. So this is get and owner, then set, and then we have delete. So if you implement either of these three methods, your class is considered to be a descriptor. If you only implement get, then your descriptor is regular descriptor, also called non-data descriptor. If you implement get and then set or delete, your descriptor is called a data descriptor. They are handled slightly differently, but for the beginning, we can disregard this differentiation. And we're gonna focus purely on get. By the way, if you want to know more, you can take a look at the descriptor guide in the Python documentation. And here in the definition section, there is the descriptor protocol specified, and with all the details. And also there are examples how to implement several pure Python equivalents. Okay, so how does it work? Let me here just print get self instance owner, and then we'll just return 42 so that we can play with this. So let me execute that. We have that A object, and now if we access that attribute of the class, which is a descriptor, instead of returning back the descriptor, Python calls the get method and returns the result. So if we access the descriptor, we see that we got 42, which was returned here. And then in the print statement, we see that self is the descriptor object. Then the instance is the A object on which we have accessed the descriptor, and owner is the class of that instance. In our case, this is A. So as you can see, this is very similar to how you would imagine properties work, and we'll see shortly how to implement our own property class, or at least a simple version that's not complete but fully illustrative. Okay, so once we know this, let's try implementing that property. So what we're gonna do, we will implement our own property class. So let's say that we have a class person, and it has a function name. And let's say that it, let's just return a fixed name like John here. And we would like to basically do this. So first of all, what we need to do, we need to define init, and we need to store the function that we are decorating. Now that we have that function, whenever we access a.name, we would like our function to be called and the result to be returned. So what we do here, we just return here that self function, and then we're gonna pass the instance here. So let's fire it up. Oh, sorry, person here. Person. Okay, so if we now try to access it, we see that we have actually called the get method, which called the function and return that value. So that's just a very simple example. Properties are more complex, like for example, you can set setters and so on, but just I think this is enough for an illustration. Okay, the next thing that I would like to show you is how methods are implemented in Python. So yeah, let's drop all that. And what we're gonna have is a class that defines a foo method that returns our own favorite number, which is 42. And then we'll create an instance. And what we're gonna do, we're gonna implement this foo method without using methods, just by using regular functions. So I'm going to do this and move it here. And here we will create a new attribute foo, and it will be a method that will be wrapping the foo function. So now we need to implement that method. We're gonna implement the get method here, and basically when we access a.foo, we would like to get that bound method object that has the function bound to the instance. So what we need to do, we need to store the function similarly as in the property example. And now what we're gonna do, we are going to use functools partial for partial application of the function. And and we are gonna to initialize it with the instance. So we are going to bind the first parameter of that function, which needs to be self, with that instance. so let's import functools, yeah, and this instance. Okay, so let's start it. And if we access a foo, we don't get that bound method directly, but we obtain the result from functools partial. We will see how to improve that soon. But the important thing is that now we can call foo, or we can store foo in another variable and call that. Now, if we wanted to get that bound method object, we can use the types module and the method type from it. So let's import types module. Let's restart. And now we get that bound method object, similarly as we would have with ordinary methods. Now, one more thing that we need to fix: if we access that foo function through the instance, we get an error. So what we need to do, the owner parameter is the class that is passed in case we basically access the descriptor through the class, the instance will be none. So if instance is none, we know that we have accessed that descriptor directly. So in this case, we are gonna just return self function. Right, so let's restart. So a foo is that bound method and a foo is that function. So if we use a function and pass a in this way, we get the desired behavior. Okay, so this is how methods work in a nutshell. By the way, all of that is unnecessary because functions themselves are already descriptors. So if we do this, this is the same as what we have done earlier. We don't have to do any dances around. We can just define a function, and since functions are descriptors, this will work. So if we reload, and if we check that a foo, we can see that it is actually a descriptor. Alrighty. In the final part, we're gonna discuss metaclasses, which is an advanced topic in Python. And let's start with the description of so-called metaprogramming. When you program, you write code that performs certain tasks which you need to fulfill. When you metaprogram, you go one level higher and you write code that either produces or manipulates code that then does the task that you need to do. This can be helpful in case you need to really go one step above and do some very generic thing, which can be in the end simpler maybe for your end users than writing the code directly. So metaprogramming is code that creates or manipulates other code. In Python and also in some other languages like Ruby or Smalltalk, we don't have just classes, but we have also something which is called a metaclass. And metaclasses are used to create classes, and classes are then used to create instances. So if we go here, what we have in many languages is that from classes you create instances, and in Python there is also a class called a metaclass that is used when producing classes. And we will see how those metaclasses work, how you can use them to modify your classes when they are being created, what are the uses, and so on. First of all, what are the uses? One use can be to implement your own plugin system in which whenever you, for example, subclass a certain class, that subclass is stored somewhere, and can be used later on. Another use case is when you want to initialize some classes or modify them. So you can create a metaclass that, for example, adds a debug statement before calling every method on the class, or something like that. Or if you are familiar with the ABC module, you can use the ABC meta class, or just the ABC class, to create an abstract virtual or abstract base class and use it to validate that subclasses implement the required methods. So these are just a few ways of using metaclasses. In Python, there are several built-in metaclasses, but the default one is called type. The naming is kind of a maybe misnomer, because when we saw type was previously used as a function for determining the type of an object, but it is actually a metaclass that is callable. And if you call it with a single argument, it will tell you the type of the object. So here is the type, and we see that it is a class, but actually it is a metaclass. And if you call type on an object, it will tell you its class. And if you call type on a class like integer, it will give you its metaclass. So in this case, it is type, similarly as for dictionary. So type is the default metaclass, and you can obtain the metaclass by calling type on a class. Okay. What should we talk next? One fairly strange thing is that you might be wondering, what is the type of type, right? Do we have some metaclasses or metaclasses? No, we do not. As we can see, that type is an instance of itself. So this is hard-coded in the interpreter. Otherwise, you will get meta classes, and yeah, so it's Python all the way down, or type all the way down. All right, enough talking. Let's see an example. So I'll give you an example which I saw in a video by David Beasley, and I very like that. It's kind of illustrative, although not very useful. But let's say that you are a fan of the Java programming language and you really like the single inheritance model, and you would like to inflict that on your fellow colleagues who program in Python. So let's say that we have a base class, then we have a class that inherits from that class, also use another one, and then what we can is to create another class that inherits from both A and B, and we would basically like to prevent that from happening. So we would like to prevent this creation. How we can do that? We can implement our own meta class. So let's call it Java Meta. We will inherit from type, so this is going to be a meta class, and we need to implement the new method. So first of all, the parameter is the meta class. Then we have the name of the class, its base classes, and then the attributes that the class should have. The meta class can be used in this way. You just need to specify the meta class keyword parameter of the class. So we're gonna here put Java Meta. And what we need to do here, we need to check that if the number of bases is basically greater than 1, meaning that there are at least 2 base classes, we raise an exception. No. Right? So let's comment this. let's start, and of course, otherwise we need to create, we need to return super new and yeah, all the parameters. All right, so now we see that we have that A and B class, and we try to create that C class. And we can see that when we were trying to create that class, we got that error. So in runtime. So in this way, it's another way of manipulating classes during runtime. And by the way, I'm not sure if you know this, but you can like add custom keyword arguments here. They will go here. And you can use them like in this code, like if you need to, but yeah, there is seldom a use case for this, but if there is, you can use that. So maybe consider this as a fun fact. Okay, now let's see how to create class manually. So let's say that we have this class foo returning 42, and what we would like to do is to create this class but without using the class keyword. So we can do that by calling type directly, and it accepts 3 arguments which correspond to the parameters of the name, new function that we saw earlier. So first of all, this is the name of the class, then a list of its, or a tuple of its base classes. So this will be just object. And then finally, we need to provide the dictionary or the attributes that the class should have. So there will be one, which will be called foo, and it will be a function that returns 42. And bam, we have a class. Similarly as we would get by using the class keyword. So we can instantiate it, and we can call foo on it. By the way, if you were wondering what's the difference between using type and between the class keyword, the class keyword is more powerful, it does more stuff. For example, it properly sets the documentation string if you would have any here on the class. It also properly sets up certain attributes like qual name and so on. And it also allows you to customize the dictionary that should be used for storing the attributes in the class by calling prepare, the prepare magic method. So it's not just a syntax sugar over the class keyword. The class keyword is actually more powerful. A minimal class can be created in this way. So we can just use the empty string, no base classes, and the empty class dictionary in this way. And here we can see that we have created a class with an empty name, which is not possible using the class keyword because Python accepts requires something there. And if we check the bases, we'll see that Python has injected the object base class because this has to be the base class in every class hierarchy. Yep. Now, you might be wondering, like, we have that type metaclass and we have that object that is supposed to be the base of every class. So, what is their relation? So first of all, let's take a look at type, and as you might expect, even type inherits from object. However, if we take a look at the type of object, we see that the object class was created from type. So this is kind of a chicken and egg problem, and this is one example where Python is being magical because you cannot express this in Python this needs to be hard-coded in the interpreter, meaning that type inherits from object, but object was created from type. Now, you might be wondering what happens when you create and instantiate a class. So we are gonna take a look at this now. Okay, so let's go with the example that we had earlier when we have created that a class and a object, and then we saw that first new is called, which creates the instance, and this instance is then passed as a self parameter to init. And we'll see how this behaves in the presence of a metaclass. So we'll see the bigger picture. So let's add a metaclass. Let's call it just metaclass meta, inherit from type. And first of all, if you look at this, it looks like a function call, right? If we had a function foo here, it's just a function call. And this is similar with that being a class. So what is actually called is the call function here. So we can print meta call, and we delegate this to the superclass type. So in this case, this method is called whenever we try to call a class. Remember that if we define this here, the call method, that would be applied when calling the objects of the class. But since we are calling the class itself, we need to go higher, one level, and put this on the metaclass. So let's start it, and we can see that first of all that metacall was called, then new and init on the class. The next step, which is called, is that new method metaclass, let's call it this, which accepts name, basis, and that class dictionary or attributes. So we're gonna print meta new, and we're gonna return super new metaclass name, basis, and headers. Let's restart, and we see that meta new was called to create the class. And what is also called, although it has fewer use cases, is init on the metaclass, basis, and attributes. So we can print meta init, and we're gonna return just super init name, basis, errors. So let's restart for the last time. So this is when the A class is being created here. This is when it is being initialized. Then when we do this, the call double underscore call method is executed, and then the instance is created and initialized. So this is a more complete picture of what is happening. And you can override any of these methods and do whatever you want. That's the beauty of Python. We already kind of saw what happens when you try to access an attribute of an object. So let's see what happens when you try to access an attribute of a class. And we can take a look at that blog post by Yonel. And there is a similar diagram here, which applies to when accessing an attribute of a class. So this needs to deal with metaclasses and classes instead of just instances and classes. once again, we will not go through all the details, but basically what the diagram is similar to the one to the diagram above. The one difference is this branch, because it needs to handle also descriptors, but otherwise it is fairly similar, and it behaves in a kind of an intuitive way. So if you need to know the details, you can look into the Python documentation or in those diagrams. And yeah, once again, if you need to overwrite any of that, it is possible via get attribute or via get attr, this time on the meta class. There are cases when metaclasses are maybe too complex or are not required to achieve what you need, and there are some simpler ways to achieve things. So let's see what these are. So first of all, class decorators. As you can decorate functions, you can decorate classes. So in this way, we could decorate our class A, and that decorator, once if we define it, it will take a class and do whatever it wants with that class and return the modified version. And then you can apply the same decorator to any other class. The downside, or well, the upside is that creating a decorator is simpler than creating a meta class and maybe more understandable. The downside is that the decorators do not propagate through class hierarchies, meaning that if you have a hierarchy, then you need to decorate every subclass, and you cannot forget about this. If you forget about this, the decorator is not applied. However, if you define a meta class, you can just specify the meta class on the base class, and they kind of propagate through the class hierarchies. Yeah, but if you want, you can create class decorators. The other functionality that can be used is the init subclass special method, which is useful, for example, when implementing the aforementioned plugin system. So let's create a class called plugin, and yeah, have a class attribute, for example, registered plugins. And then we can define that init subclass function. Always, if you are unsure, init subclass function, what it is, yeah, you can basically see this here. So yeah, basically that's the class. So what we're gonna do, we're gonna plug in registered append and class, and then we're gonna create class plugin A, plugin, and we're gonna create plugin B, and we can execute it, and then we can take a look at the registered plugins, and we see that for both of these classes the init subclass function was called, so the list contains both of these classes. So that can be useful in this case. Third, we have the special method setName, which is used often on descriptors. So let's say that you have a class A and you would like to create 3 descriptors. So my descriptor, and what usually was the case before Python started supporting setName is that you had to pass the name of the descriptor in here. So if you do this and that, you can accidentally forget about changing this, as I did right now. So to simplify this, when creating my descriptor class, you can specify that set name. Once again, it is described in the Python documentation. So here you can see what it accepts: self, owner, and name. Self, owner, and name. And in this way, let's just print the name. And this function is called whenever a new descriptor is assigned to an attribute. So if we do this, we see that we get printed A and B and C. So the descriptor can then know its name, which can be useful, and also eliminates certain use case when you would you would use a metaclass instead. And finally, there is the good old code generation, where you can basically create your program as a string, manipulate with it with string operations, and then using the exec function to execute the code. So we can exec, for example, print 1 + 1 as a string, and we can see that it executed it. This can be faster than using metaclasses or the other machinery, and in some cases it can be simpler, but beware that providing untrusted inputs into exec can lead to vulnerabilities, because you need to take the good care that you escape everything. So it can be less secure than using metaclasses, but in some cases this is useful. And for example, exec is used in the implementation of named tuple from the collections module. So even the standard library uses this approach. But beware of security holes when using exec or evol or any other method that evaluate strings. Okay, we made it. So this is the end of the talk. In the slides there are some references and links to your further reading and watching. So there is a link to the data model description in the official Python documentation. It is more a reference guide, but if you are unsure about anything, so for example, what are the parameters of a set name, you can check this out. Then there is the documentation on descriptors. There is a simple explanation. Then there is the technical tutorial of how it works and what is the descriptor protocol, what are the methods that you can basically create. And it also provides pure Python equivalents for various parts like properties, functions, methods. We have seen those too, but we can also implement class methods, static methods, and so on via descriptors. And then there is also the documentation in the types module, in which we have that method type, which we have seen. Then there's this blog post by Yonel, which I like very much, and the diagrams there are quite illustrative. Then there is a blog post by Evie on object models, where several object models are described, for example, of Python, JavaScript, or Lua. So check it out. Then there is another, in this case, presentation or slides. Then there is an article which describes metaclasses and classes of what is happening in greater detail. And finally, if you like watching more than reading, I can recommend this 3-hour tutorial by David Beasley on Python 3 metaprogramming. Now it's quite old, but it is still relevant, and it uses Python 3.3, so it is, I would say it is up to date. It doesn't use Python 2, it uses Python 3, so I can highly recommend it. And then there is a talk by Mark Smith on metaclasses, which is only 1 hour long, and I can also recommend that. All right, so this is all. Thank you for your attention, and see you next time.